Welcome everyone. Today's session is 60 minutes, 45 minutes of content, 15 minutes for Q&A at the end. We're going to cover the full picture of H3C's AI-ready data center networking story, why lossless Ethernet matters, how RoCE compares to InfiniBand, H3C's full switch portfolio, and then the DDC architecture, which is H3C's flagship AI cluster technology. If you sell or influence any data center deals, this session will give you the language and technical grounding to have confident conversations with customers who are building or planning AI infrastructure. We'll have 15 minutes at the end for questions, and please save them, and we'll go through everything then. Let me start by setting the scene. Let me start with why we're all here. The data center market has changed more in the last 3 years than it did in the previous 15. The numbers are striking. AI training compute grew more than 300,000 times between 2012 and 2018 per OpenAI's analysis, and has kept accelerating since. To put that in perspective, the compute used to train GPT-2 in 2019 was already considered large scale. Today's frontier models from OpenAI, Anthropic, Google, and Meta use thousands of times more compute than that. And we're not just talking about training anymore. There are now 3 distinct AI workloads driving data center infrastructure decisions. First, training, building the model from scratch or fine-tuning it. Second, inference, serving the model to end users. This is now as GPU intensive as training was 3 years ago. Third, MOE, or mixture of experts models, a newer architecture used by models like DeepSeek, which fires only a subset of model parameters per token, but creates complex all-to-all communication patterns between GPUs. All 3 of these workloads stress the network in ways that traditional data center infrastructure was never designed for. The customers you talk to every day, whether they're building private AI clouds, upgrading their DC infrastructure, or just asking how to prepare for AI workloads, they're all facing this challenge. The good news for H3C channel partners is that the network layer is where the opportunity is, and H3C has a complete end-to-end story to tell here: switching, management, compute, and storage. That's what we're covering today. Let me make this concrete with a simple formula. Your customer's effective AI cluster performance equals GPU compute per server, multiplied by the number of GPUs, multiplied by network efficiency, multiplied by availability. Network efficiency sits right in the middle of this equation. If the network drops to 90% efficiency, which is very easy to achieve with the wrong configuration, every single GPU in the cluster underperforms by 10%. 100 million Rand GPU cluster is effectively worth 90 million Rand. And that's the good case. The 3 AI workloads hit the network differently. Training uses a communication pattern called all-reduce. At the end of every training step, GPUs exchange gradient information using a ring or tree pattern. Each GPU talks to its neighbors, not every GPU at once. It is bandwidth optimal precisely because it is not all-to-all. But it produces a small number of very large synchronized elephant flows, and if any of those flows hits congestion, the training step waits for the slowest pair to finish. That's the tail latency problem. Inference is different. The bottleneck is KV cache prefill, where large tensors move between GPUs per token. Latency matters here at every single inference request. MOE models add a third pattern, expert dispatch and combine, where tokens are routed to different GPUs for processing and then collected. This creates unpredictable bursts that simple per-flow load balancing can't distribute efficiently. The common thread across all 3 is this: you need a lossless, low latency, high bandwidth network, not a best effort network, a lossless one. That's what the rest of today's session is about. For 2 decades, the standard answer for high performance compute networking was InfiniBand, a proprietary protocol from Mellanox, now owned by NVIDIA. InfiniBand has excellent performance characteristics, low latency, high bandwidth, native RDMA, but it comes with significant constraints: proprietary cables, proprietary NICs, proprietary switches, proprietary management, and a price premium that reflects all of that. The alternative that has emerged over the last 5 years is RoCE, RDMA over converged Ethernet, specifically the 2nd generation called RoCE version 2. RoCE version 2 delivers the same key capability that made InfiniBand attractive, RDMA, which stands for Remote Direct Memory Access. RDMA allows one GPU server to read or write directly into the memory of another GPU server without involving either machine's CPU. This dramatically reduces latency and CPU overhead for collective communications. RoCE version 2 does this over standard UDP IP Ethernet, using the same cables, the same switches, the same management tools as the rest of your IP network. The industry has voted with its wallets. Meta is the most cited example. For Llama 3, they built two 24,576 GPU H100 clusters, one on RoCE Ethernet and one on InfiniBand, to compare them head-to-head, proving RoCE is viable at frontier training scale. Note their RoCE cluster used Arista and OCP switches, not H3C, so cite it as proof that RoCE works at scale, not as an H3C reference. Multiple hyperscalers have built or are building large RoCE-based AI training clusters. NVIDIA themselves now sell RoCE-capable ConnectX NICs alongside their InfiniBand products. The question for your customers is no longer InfiniBand or RoCE. The question is, which RoCE network should we build? And H3C has a full RoCE switch portfolio spanning every tier of the AI fabric. The term lossless Ethernet sounds straightforward, but lossless rests on two core mechanisms, PFC and ECN DCQCN, plus DCBX, which automates their negotiation across the fabric. The first is PFC, Priority Flow Control, IEEE standard 802.1 QBB. PFC works at the switch buffer level. When a buffer is about to fill, the switch sends a pause message to the upstream device, the NIC or the connected switch, to temporarily halt traffic on that specific priority class. This prevents packets from being dropped due to buffer overflow. Why is this critical for RDMA? Because RDMA is extremely intolerant of packet loss. In TCP, if a packet is lost, TCP retransmits just that packet. In classic go-back-N RDMA, a single lost packet forces retransmission of all in-flight data after the last acknowledgement, up to a full bandwidth delay product of data, not just that one packet. Newer NICs soften this with selective retransmission, but the penalty is still far worse than TCP, which is why lossless matters so much more for RDMA. PFC prevents that. The second is ECN, explicit congestion notification. Instead of waiting for the buffer to fill and then pausing, ECN marks packets as they pass through a switch that's beginning to feel load. The receiver reads these marks and signals the sender to slow down before congestion becomes a problem. H3C implements this with DCQCN, Data Center Quantized Congestion Notification, which is specifically tuned for RoCE traffic patterns. The third is DCBX, Data Center Bridging Exchange, carried over LLDP, IEEE 802.1AB, and standardized in IEEE 802.1 QAS. It is the glue that makes PFC and ETS automatic, running between the NIC and the switch, automatically negotiating which traffic priority classes get PFC protection, which get bandwidth guarantees via ETS, and which are treated as best effort. Without DCBX, you can still run lossless with static configuration. Meta does exactly that. But every NIC and switch port must be set by hand, and a single mismatch breaks negotiation. DCBX lets the fabric self-configure and stay consistent. H3C supports all three on every AI positioning switch in the portfolio. One of the common objections you'll hear from customers considering RoCE is, has anyone actually proven that it performs as well as InfiniBand? The answer is yes, and the proof comes from an independent third-party test lab called the Tolly Group. H3C commissioned Tolly to run a head-to-head comparison of H3C's RoCE network against InfiniBand. The test used NCCL tests, the standard NVIDIA Nickel benchmark suite used by the AI industry to measure collective communication performance. The test measured all reduced bus bandwidth using 8 nodes each equipped with NVIDIA H100 GPUs. The results were clear. At a 16 gigabyte data size, a typical gradient exchange for a large language model training step, H3C's RoCE network delivered bus bandwidth within 0.73% of InfiniBand. In most configurations, RoCE and InfiniBand were statistically indistinguishable. They also ran a practical training test. They measured the tokens per second throughput of training a Llama 370B model on H3C RoCE versus InfiniBand. The results were near identical throughout the full training run. This is important because it's not a synthetic benchmark, it's an actual model training workload. The conclusion: if your customer is holding off on a data center upgrade because they believe InfiniBand is the only option for AI training, the performance objection has been independently disproven. Enterprise Ethernet is now a fully credible AI training interconnect, and unlike InfiniBand, it uses standard hardware, standard protocols, and integrates with the customer's existing IP infrastructure. I can share the Tolly report numbers. Reports 24168, 225106, 225111, and 225112 with anyone who wants to take these back to a customer or use them in a proposal. Let me explain the ECMP problem because it's central to understanding why H3C's ADDC and DDC architecture exist. ECMP stands for Equal Cost Multipath Routing. It's the standard way that switches load balance traffic across multiple paths. When a packet arrives, the switch looks at its source IP, destination IP, source port, destination port, and protocol, the 5-tuple, and runs a hash function. That hash result picks one of the available paths. The same flow always goes the same way. This works reasonably well for traditional web application traffic where flows are long-lived, diverse, and naturally spread themselves across paths over time. AI training traffic is completely different. Consider an all-reduce across 100 GPU nodes. Ring-tree all-reduce produces a handful of very large synchronized flows that all start at nearly the same time and have similar 5-tuples. They're often going to the same destination IPs and therefore hash to the same paths. The result is that some links become saturated while others sit idle. The bottleneck flows cause the entire all-reduce operation to wait. One slow flow stalls the entire training step. This is the hash collision problem. MOE inference makes this worse. The expert dispatch pattern sends thousands of short burst flows simultaneously across the fabric. These short flows are almost impossible to distribute evenly with 5-tuple hashing. They arrive and depart faster than the hash table can adapt. An inference disaggregation creates a third pattern: prefill nodes and decode nodes exchanging large KV cache tensors in unpredictable bursts. Customers who have deployed traditional ECMP-based fabrics for AI training consistently report that GPU utilization is lower than expected, often 60–70% effective utilization on hardware rated for 100%. The gap between rated and effective utilization is the ECMP tax. H3C's answer to this is path intelligent routing, which we'll cover in the ADDC slides. This is the section divider for the H3C DC switch portfolio. Pause here, invite the audience to note where they are in the agenda and briefly preview what's coming. We're going to walk through the full switch stack from the 25G Tor layer up to 800G spine and into the DDC cluster fabric. Every product we show has been confirmed on H3C's international product pages and carries full RoCE version 2 PFC and ECN support. Feel free to slow down on the product slides that are most relevant to your current customer discussions. Let me give you a map of the H3C data center switch portfolio before we go into individual products. H3C covers the complete AI fabric stack from the server access layer all the way up to a DDC cluster fabric. Understanding which switch serves which type of server is key to a confident pre-sales conversation. At the general compute access layer, the S6850, 56HF, and S6825, 54HF are 25G switches for CPU servers, storage nodes, and inference hosts. The majority of servers in any enterprise DC. These run RoCE version 2, PFC, and ECN at the access tier. At the GPU AI training server access layer, GPU servers with 400G or 800G NICs connect directly to the spine. The S9827 series 800G or S9825 series 400G or to the S12500 AI NCP modules in a DDC deployment. There is no intermediate 25G hop for GPU training traffic. This is a critical distinction to understand for any AI DC design conversation. Above the access layer sits the spine. H3C offers 3 spine tiers: the S9825 series at 400G, the S9827 series at 800G, and the S9855 series for mixed 200G, 400G densities. The S9827 can also serve as the direct access switch for GPU servers, not just spine. Above that sits the DCI and core routing tier, the S12500R and S12500CR, with deep buffers for AI burst traffic. And at the top of the pyramid is the S12500AI, H3C's DDC cluster fabric, H3C's implementation of the open distributed disaggregated chassis architecture for deployment scaling beyond standard box-to-box limits. Every switch in this stack supports RoCE version 2, PFC, ECN, ETS, and DCBX. The design principle is consistent, BGP, EVPN, and VXLAN throughout, no proprietary overlay protocols. The S6850 56HF and S6825 54HF are H3C's 25G data center access switches for general enterprise DC workloads, standard compute servers, storage nodes, and inference hosts. I want to be explicit about where these switches fit. They are not the access switch for high-density GPU AI training servers. AI GPU training servers equipped with 400G or 800G NICs connect at the S9827 spine layer, or directly into the S12500AI NCP modules in a DDC deployment. The 25G and 100G port speeds on the S6850 and S6825 are the right match for enterprise CPU servers, NVMe storage arrays, inference serving nodes, and general DC workloads, the vast majority of servers in a data center that are not running GPU training jobs. The S6850 56HF gives you 48 ports of 25GE SFP28 for server connections and 8 ports of 100GE QSFP28 for uplinks to the spine, 48 server connections in 1U. The S6825 54HF is similar, 48 ports of 25GE and 6 ports of 100GE uplinks. Both switches are confirmed on H3C's English website with no EOS notice. Both carry the full lossless suite, RoCE version 2, PFC, ECN, ETS, and DCBX. The DCBX auto configuration negotiates lossless parameters with the NIC automatically, no per port manual config. For the partners here, the most common first AI DC conversation is actually this layer. A customer expands their DC for AI, but most of their servers are still CPU-based inference hosts, storage nodes, and general compute. The S6850 and S6825 covers that layer at the right price point with the right feature set. When they scale to GPU training clusters, that's when you introduce the S9827 or DDC conversation. Understanding which servers go on which switch is part of your pre-sales positioning. It avoids both overspec at the general access layer and underspec at the GPU training layer. The S9825 is H3C's 400G spine switch, and it's the workhorse of mid-scale AI training fabrics. The S9825 64D gives you 64 ports of 400G QSFP-DD in a single switch, 51.2 terabits per second of total switching capacity. The latency figure that matters most for AI training is the store and forward latency, and H3C publishes sub-microsecond latency for this switch, less than 1 microsecond. Why does sub-microsecond latency matter at the spine? Because in an all-reduce operation, a gradient tensor from GPU node A travels from its NIC through the tier R, through the spine, through another tier R, and into GPU node B's NIC. In a large cluster with hundreds of GPU nodes, there can be thousands of simultaneous flows doing this. Each extra microsecond of spine latency adds to the tail latency of the all-reduce. Over thousands of training steps, this compounds. The S9825 64D also carries 56 megabytes of buffer for burst absorption during collective communications, important when thousands of flows arrive simultaneously. The S9825 128B is the 200G variant, 128 ports of 200GE QSFP56, also 51.2 terabits total. This is useful for customers who have 200G NICs in their servers and want to match port speeds without overspending on 400G uplinks. Both support INT, in-band telemetry for real-time per-packet congestion visibility, and both pair natively with the ADDC controller for path-intelligent routing. which we'll cover shortly. In a typical 400G AI training fabric design, the S9825-64D serves as the spine switch, the S6850 or S6825 serves as the TOR, and DDC optimizes the path selection between them. Source: www.h3c.com in Products and Solutions, Interconnect Switches, Products Data Center Aggregation, S9800 H3C, S9825, Local Datasheet S9825 DMD, downloaded 2026-0505. The S9827 is H3C's 800G spine platform, and it comes in 3 models. I want to be precise about the naming because the 3 models use different port types. The S9827 64E has 64 ports of QSFP DD800, that's QSFP DD with 800G per port in a 2U form factor. The S9827 64EP has 64 ports of OSFP 800, OSFP, a different connector form factor, also 800G per port, in a 4U form factor with N plus N power redundancy. The key difference between 64E and 64EP is the connector, QSFP DD for the 64E, OSFP for the 64EP. Both deliver 800G per port. The third model, the S9827 128DH, has 128 ports of QSFP 112. And I want to be clear here, QSFP 112 ports on the 128DH are 400G per port, not 800G. The total capacity is the same, 102.4 terabits, achieved through higher port count at 400G rather than lower port count at 800G. If a customer asks about the 128DH, make sure they understand that port distinction. All 3 models carry H3C's full AI networking feature set: RoCE version 2, PFC, ECN, and something called AI ECN, H3C's enhanced congestion notification algorithm tuned specifically for the burst patterns of GPU collective communications. They also support INT telemetry, gRPC, and ERSPAN for full network observability. It's designed to interoperate with NVIDIA CX series NICs. Confirm specific CXA6, CX7 validation on H3C's current compatibility matrix before quoting it to a customer. The S9827 is the right spine choice for customers building next-generation 800G AI fabrics, or for customers who want to future-proof their spine investment while their servers catch up to 400G and 800G NIC densities. The S9855 series addresses a very specific real-world scenario that comes up often in enterprise AI deployments. A customer has a mix of GPU servers, some have 200G NICs, perhaps first-generation H100 servers with NVIDIA CX6 NICs, and they're adding new servers with 400G NICs. They don't want to run 2 separate spine layers with different hardware, but they also don't want to pay for 800G ports that they don't need yet. The S9855 series solves this. The S9855 24B8D has 24 ports of 200G QSFP56 and 8 ports of 400G QSFP DD in one switch. A mixed density spine that serves both NIC generations from a single platform. The S9855 32D gives you 32 ports of 400G QSFP DD if you're standardizing on 400G uplinks. Both carry the full lossless suite, RoCE version 2, PFC, ECN, ETS, and DCBX, which makes them relevant for RoCE workloads. Note for accuracy: the S9855 family on H3C.com lists PFC, ECN, and ETS, but not a distinct AI ECN feature, so don't claim AI ECN for this family. The S9855 series is the right answer when a customer says, we have a mix of 200G and 400G in our cluster, and we want to use one switch type for the spine. It's also a cost-effective entry point for customers who don't yet need full 800G spine bandwidth. The S12500R and S12500CR are H3C's data center core and DCI switch router platform. This is a different class of product from the spine switches we've just covered. This is a modular chassis platform designed for the largest DC cores and for connecting multiple data centers together over WAN links. The headline capacity is up to 5,806 terabits per second, that's 5 petabits, which positions it at the very top of the industry for DC routing. But the feature I want to highlight for AI workloads is the deep buffer. The S12500R has up to 1600 milliseconds of burst absorption per 10G port. Why does this matter for AI? AI training traffic is inherently bursty. All reduce operations send large bursts of gradient data in synchronized waves. If those bursts arrive at a DCI link faster than they can be forwarded across the WAN, packets are dropped and retransmits happen. A 1600 meters buffer absorbs those bursts instead of dropping them. For inter-DC AI training, where a customer is running GPU pools in two different data centers and training across them, this deep buffer is essential for maintaining lossless delivery across the WAN boundary. The platform also supports MACsec on all line cards for link-level encryption and SRv6 for traffic engineering across the DCI fabric. RoCE is supported on the platform, meaning lossless RDMA can extend across DC boundaries. For carrier customers or large enterprises with multi-site AI training infrastructure, the S12500R is H3C's answer for the core and DCI tier. This is the section divider for the DDC architecture. Take a moment to set expectations for the audience. DDC is one of H3C's most differentiated platforms in the AI networking space, and it's also the most conceptually different from traditional switching. Let the audience know that we're about to step beyond box-to-box switching into a fabric-scale AI cluster architecture. DDC is the open, OCP-rooted, distributed, disaggregated chassis approach, and H3C's S12500AI is H3C's implementation of it. Reassure them that DDC is not required for every AI DC deal. It's the answer for the largest scale deployments. For most channel partners, the value of understanding DDC is that it gives you a credible answer when a customer asks, what happens when my cluster needs to scale beyond what a box-to-box fabric can support? That answers H3C's S12500AI DDC platform. Let me explain DDC, diversified dynamic connectivity, from first principles. DDC, distributed disaggregated chassis, is an open OCP-rooted architecture introduced by AT&T in 2019 and built on Broadcom DNX merchant silicon that solves a problem critical at very large GPU cluster scales, the limits of flow-level load balancing. H3C markets its implementation as diversified dynamic connectivity, and the S12500AI is H3C's realization of it. In every traditional switch, traffic is load balanced at the flow level. A flow is a network connection from one GPU to another. Each flow is assigned to one path through the network using ECMP hashing. The problem is that in AI training, all the GPU to GPU flows in an all-reduce operation start at the same time, have similar characteristics, and tend to hash to the same paths. This creates hot links. Some paths are 100% utilized while others sit idle. In a small cluster, this is manageable. At thousands of GPUs, it becomes a severe performance bottleneck. DDC solves this by moving the unit of forwarding from the flow level to the cell level. A cell is a small fragment of a packet. Think of it like cutting a letter into tiny pieces. Each cell is independently routed across the fabric. Because each cell is independent, consecutive cells of the same flow can take different paths. All paths in the fabric are used simultaneously and fairly. There's no flow level hash and therefore no hash collision. Head-of-line blocking is eliminated by per egress virtual output queues, VOQ, and a request grant scheduler keeps delivery fair and collision-free, so a large flow doesn't block smaller flows behind it. The physical architecture separates two functions that are combined in a traditional switch. The NCF, Network Connectivity Fabric, handles the distributed switching fabric and spans across racks. The NCP, Network Connectivity Processor, handles the connection to AI servers. This separation is what allows the fabric to scale beyond the physical limits of a single chassis. Let me compare the DDC architecture to traditional box-based switching to show where the scale advantage comes from. In a traditional two-tier box-to-box fat tree, you top out at roughly 8,400 G ports. This is confirmed by H3C's own training materials as the realistic maximum for box-to-box topology. A box-to-chassis topology extends this to around 36,400 G ports per H3C technical guidance. These are real achievable scales for enterprise AI DC deployments. At these scales, ECMP hash collisions are measurable and impact GPU utilization in production clusters. DDC removes the scale ceiling and the ECMP problem simultaneously. The S12500 AI NCFN fabric nodes and NCP access nodes are added incrementally. The cluster grows by adding physical units without redesigning the topology. Real production deployments give you a sense of scale. One large AIGC operator's DDC deployment runs 9 NCF nodes plus 40 NCP nodes, providing 440 400G ports for 180 GPU servers with 8 cards each. Another runs 2 NCF plus 8 NCP nodes for 288 400G ports across 36 GPU servers. DDC supports 400G and 800G server connections in both the K-series, first-gen 200G NCF interconnects, and N-series second-gen 400G, 800G NCF interconnects. The key advantage is not just scale, it's that at any scale, DDC delivers cell-level load balancing. Every path in the fabric is used simultaneously and fairly. There is no ECMP hash table and therefore no hash collision. In a large all-reduce with 100 GPU nodes, all 100 paths are used concurrently. The bottleneck that kills GPU utilization in hash-based fabrics simply does not exist. The decision guide. For clusters up to roughly 8K GPUs, S9827 box-to-box with ADDC path optimization is the right answer. For larger clusters or for customers who have measured ECMP collision loss as a production problem, DDC is the answer. Deployment examples from H3C 2026 H1 Data Center Product Strategy, Slide 36. The S12500 AI product line consists of 3 models, each serving a distinct physical role in the DDC architecture. The S12500 AI NCFN is the NCF fabric node, the 7U chassis that forms the distributed switch fabric. Multiple NCFN nodes are deployed together to form the full fabric layer of the DDC cluster. The S12500 AI 36DH20EP NCPN is the NCP compute access node, a 2U unit that connects GPU server rows to the NCF fabric. It has 36x 400GE QSFP112 service ports plus 20x 800GE OSFP uplinks to the NCF fabric. The S12500 AI 18D48B NCPK is another NCP model with a different port balance for higher server density in certain deployment configurations. All 3 carry the full AI networking feature set: DDC cell level forwarding, RoCE version 2, PFC ECN and AI ECN. I want to give you some honest channel guidance here. The S12500 AI is not a standard switch cell. A customer who needs DDC is building a large GPU cluster. We're talking tens of millions or hundreds of millions in infrastructure spend. These deals require joint pre-sale scoping with H3C's own architects. The design involves rack-level planning, NCF and NCP ratio calculations based on GPU count and topology, and typically integration with H3C's server and storage platforms. If you have a customer who is asking about AI cluster networking at this scale, the action item is to get H3C pre-sales engaged. That's the conversation I want to have with you. Bring me the opportunity and we'll work through the design together. You should also verify with your H3C distributor that the S12500 AI is available and priced for your market before including it in any quote. ADDC, Application-Driven Data Center, is H3C's intelligent network management and path optimization platform for AI fabrics. The core insight behind ADDC is that the network controller can make better path decisions than static ECMP hashing if it knows what traffic patterns are actually flowing through the fabric. ADDC has 2 components working together. The first is the AD agent, a lightweight piece of software installed on each AI training server. The AD agent monitors the server's actual outbound traffic patterns in real time, which GPUs it's communicating with, at what bandwidth, with what timing. It reports this information to the second component, the ADDC controller. The ADDC controller sits at a central point in the management plane and maintains a global view of the entire fabric, which links are loaded, which paths are available, and what traffic patterns are active. When the AD agent on a GPU server reports that an all reduce is starting, the controller calculates the optimal path, for that service collective communications, a path that avoids congested links and complements the other flows already in flight. It pushes that path decision back to the AD agent, which influences how the server's NIC sends traffic. The result, measured by the Tolly Group, an independent test lab in testing commissioned by H3C in report number 225112, is a 22.33% improvement in all reduced bus bandwidth compared to standard ECMP, presented as a per-report figure rather than a broadly established fact. This is not a theoretical improvement. It was measured on real hardware with real nickel collective communication workloads. For your customers, translate this directly. If they have a GPU cluster, ADDC makes it effectively 22% more productive without buying a single additional GPU. In a world where a single H100 GPU costs around $30,000, 22% better utilization across a cluster of 100 GPUs is worth $600,000 of GPU spend that doesn't need to happen. I want to spend a moment on what makes ADDC different from other management platforms, because the feature that stands out for me is the network simulation capability. Most network management platforms include a simulation mode, or what-if analysis, that uses algorithms or approximations to predict how a configuration change will affect the network. ADDC simulation builds a virtual model of the production fabric from the actual topology and configuration of your customer's switches. When the customer wants to test a firmware upgrade or a new topology configuration or a change to ECN thresholds, they do it on the virtual replica first. If the virtual test causes a problem, they catch it before it hits production. If the virtual test passes, they have high confidence the production change will also pass. This matters enormously for AI training infrastructure where any network outage interrupts a training job that may have been running for days. The second feature I want to highlight is third-party access layer support. ADDC can manage switches from other vendors at the access layer. It doesn't require a forklift of the customer's existing access infrastructure. This is an important conversation opener with customers who already have a significant investment in their current switching estate. The third feature is the one-click pre-training stress test. Before starting a long training run, the customer can trigger ADDC to verify that the entire fabric is delivering lossless performance, PFC, ECN, and path distribution, all validated in a synthetic stress test. This is the equivalent of a pre-flight checklist for AI training infrastructure. Finding a misconfigured PFC domain with this tool is far faster than discovering it by debugging a failed training job. The end-to-end visibility features of ADDC are worth covering separately because they address a pain point that almost every AI infrastructure team experiences. When a training job runs slower than expected, the debugging process is painful. Is it the GPU? Is it the NIC? Is it the network switch? Is it the storage? Without correlated visibility across all these layers, the team is guessing. ADDC integrates monitoring across all 4 layers into a single pane. At the GPU server layer, it monitors utilization per GPU, memory consumption, job assignment, and network counters on the NIC. At the network fabric layer, INT, in-band telemetry, provides per-packet path tracing across the entire fabric in real time. INT doesn't just tell you average utilization per link, it shows you which specific flows are experiencing congestion, at which switch, at which port, at which moment during the training job. At the storage layer, ADDC monitors NVMe OF and storage access paths, because many apparent network slowdowns are actually storage I/O bottlenecks. At the optical layer, H3C's telemetry can localize a degraded optical transceiver across a large fleet of optical modules, catching a marginal transceiver before it fails completely. The ability to trace a slow training job by task ID back to a specific network bottleneck hop is particularly powerful. In a traditional environment, an engineer would spend hours correlating logs from different systems to find the bottleneck. ADDC correlates it automatically and presents the root cause. For customers who are already running AI training infrastructure, this capability alone is a compelling reason to deploy H3C switches and ADDC. The operational savings in debugging time are significant. Let me address something that sophisticated customers will raise. If DDC is a disaggregated fabric architecture, how is it different from the proprietary fabric lock-in customers are trying to avoid? It's a fair question. DDC itself is an open industry architecture. Cell-level forwarding with VOQ runs on Broadcom DNX merchant silicon and is standardized through the OCP. H3C's value is its S12500 AI implementation and ADDC tuning, not a closed forwarding scheme. But everything around DDC is built on open standards. The control plane uses BGP EVPN and VCI LAN, the same IETF standardized protocols that customers already use everywhere in their IP infrastructure. There are no proprietary overlay protocols required. The access layer is open. ADDC manages existing switches from any vendor at the access layer. If a customer has already invested in their access switching, they don't need to replace it to deploy H3C at the spine and core. The management programmability is standard. OpenFlow, gRPC, NetConf Yang, all industry standards. The NIC ecosystem is open. H3C switches are validated with NVIDIA, Intel, Broadcom, and AMD network adapters. Any standard RoCE version 2 capable NIC works. And the disaster recovery architecture is standards-based. 2+1+1 cold standby, active-active DCI, cross-DC fabric expansion, no proprietary DR protocols required. The practical message for your customers: H3C's AI fabric uses standard protocols where standards work and proprietary innovation where standards haven't caught up yet. The customer gets H3C's DDC performance advantage without locking their operational model into H3C specific tooling. That's a materially different proposition from proprietary overlay fabrics that require proprietary NICs, proprietary management, and proprietary everything else. Let me close the content portion of today's session with the partner opportunity framing. The AI data center market is not a future opportunity. It's happening now in your territory with your customers. Every enterprise customer who is building new DC capacity or refreshing existing DC infrastructure is asking about AI workloads. Even customers who don't consider themselves AI companies are facing pressure from their boards and business units to prepare their infrastructure for AI workloads. The design decisions being made right now, which switch vendor, which management platform, which fabric architecture, it will be locked in for 5 to 7 years. That's the window you're operating in today. H3C's position in this market is strong. We have a complete AI DC stack, switches from TOR to DDC cluster, ADDC management and optimization, H3C AI compute servers, and H3C Unistore storage. We have third-party testing from the independent Tolly Group, commissioned by H3C, showing H3C RoCE at near parity with InfiniBand. We have H3C's S12500 AI, a strong AIGC tuned implementation of the open DDC architecture with full RoCE version 2 lossless support and ADDC management, competitive with other DDC offerings while keeping the control plane on open BGP EVPN and VXLAN. And H3C is named in Gartner's 2025 Magic Quadrant for Data Center Switching, published in March 2025. The opportunity is real, the portfolio is ready, the pre-sale support is available. What's needed is for H3C channel partners to start having these conversations with customers and to have those conversations with confidence. That's the purpose of today's session, to give you the knowledge and the language to be the most credible voice in the room when your customer's CTO asks about AI networking. H3C commissioned Tolly Group reports, H3C training materials. To close, I want to make sure everyone in today's session knows exactly how to turn this knowledge into pipeline. Register your AI DC opportunities with H3C. Project registration protects your deal. It ensures that if another partner or H3C's own team is speaking to the same customer, you have first right to that deal. For demo requests, if you have a customer who wants to see H3C RoCE or ADDC in action, contact me directly. I can arrange a demonstration either virtual or in person. The demo is highly effective because it shows the path optimization improvement and the management platform in a live environment. For large-scale AI cluster opportunities, customers who are talking about hundreds or thousands of GPUs or who are asking about DDC specifically, H3C can arrange a visit to China to see DDC and RoCE Fabric running in full production scale. These are live environments running tens of thousands of GPUs. Seeing it at scale is genuinely different from hearing about it in a webinar. These visits are reserved for serious qualified opportunities, and I can help you assess whether a customer engagement is at that stage. My contact details are on screen. please reach out directly. I'm your pre-sales resource and I'm here to help you win deals. The H3C Tech Talk series continues with future sessions on campus switching, wireless, security, and compute. Stay engaged and keep the momentum going.